Can you see my screen?
Yes, sir.
All right. So we were discussing Taylor's formula. All right. So we have defined a polynomial P. So yeah, so let me recall this one. Given a function f from, let's say, a, b to r, such that f prime, f n, all the derivative up to n are continuous on AB, and right, continuous in AB, then we can, so given this one, we have defined a polynomial P x, which looks like at some point x, yeah, that is fine, but you have to fix. We define a polynomial corresponding to point x naught in AB as f of x naught plus f prime x naught times x minus x naught plus f double prime x naught by 2, which is also factorial 2, x minus x naught square, and so on. And the last term is fn x naught by factorial n x minus x naught or n. All right. So this one. So we have defined a polynomial like this, right? So note that p prime x naught is equal to, px naught equal to f of x naught, p prime x naught equal to f prime x naught, en x naught equal to fn x naught, right? So p is a polynomial where the derivatives it is created in such a way that the derivative up to the order n at x naught is same as the derivative of f up to the order n. All right. So the derivative matches. And we have seen that this is a unique polynomial satisfying these properties. All right. Now Taylor's formula is, let me give a geometric interpretation, which is approximation of f by polynomial. What sense? So suppose this is the graph of f. So it will not be straight. So it should erase and yeah. So this is graph of f. This is x-axis. This is y-axis, and this is the point 0. Now, zeroth order approximation would be, so we'll approximate around the point origin. So at this point, we look at this line parallel to x-axis. This is the line is y equal to f0, right? So this is the first order of approximation of the graph f. Actually, it looks like let me make it a little more clear, get the clear picture. Like this. So suppose f is like this, so that it is not like vertical. So this is this gives the first order of approximation. This one gives the, actually not the first order, zeroth order of approximation. Right, so what would be the first order? Can you guess?
f0 plus f dash 0 x.
Right, which is the line, which is what line? Which is the line which is tangent. Right, this is how the polynomial p is defined, and that will be this line. This line. So this will give the, so this is y equal to f0 plus f prime 0 x, x minus 0, which is x. Right, so this gives the, this gives the first order of approximation. I'll make these things precisely. What does this mean? Okay. So this approximation hold in a small neighborhood of the origin. So this holds in a small neighborhood of origin. And similarly, let's look at the next one, which would be something like so. Something like this. So this will give a little more closeness. So this gives you which is P1x. We can define this. Yeah, so we can define P1. This is P0 x. This is y equal to f0. Wait, y equal to f0 plus f prime 0 x plus f double prime 0 by 2 x squared. This gives second order of approximation. Yeah, so what do you think it means by this first order, zeroth order, first order, second order of approximation? So you see, this is getting closer to the curve, right, around in the neighborhood of the origin. But is this clear from the picture? That as you increase the degree of the polynomial, this is getting closer and closer to the graph of f, right? Now let me explain what I mean by closer to as it go. I mean closeness. So zeroth order of approximation means for every, so this comes from here. P approximates up to the zeroth order. For every epsilon, there exists delta greater than 0 such that mod of fx minus px less than epsilon for all x in here in this case it is 0, so in this case minus delta to plus delta in this case. But in general, so maybe I should put a definition here. A polynomial P is said to approximate the function of up to function f up to the order k if near point x equal to x naught if for every epsilon greater than 0 there exists delta greater than 0 such that mod x minus x naught less than delta implies fx minus px less than epsilon f prime x minus p prime x less than epsilon f kx minus p kx less than epsilon for all x. This is fine. Yeah. So is this correct? So is this clear? So what it means to approximate up to order k, it means it will just not just the function approximate, the corresponding derivatives also are very close. Right? So not just the functional value to be closed, the corresponding derivatives will also be closed. And this happens in this case. That is the standard polynomial which will approximate f near the point x naught. You see at x naught the derivative are equal. We want this is one standard one that will approximate. Is this clear? So there might be some other polynomial which will approximate the function up to order k or order n, but this is the very standard one example which is very easy to find from the derivatives of f. Is this clear? Is this part clear, this picture? And yeah, this picture and this definition. Is this clear?
Yes, sir.
So we are trying to approximate. You see here, it is very easy to see, right? So this, look at this one, x minus x naught. So if you look at the derivative px p prime x minus f prime x, px minus fx is this one, right? So here, see here, so yeah, so the interesting point here is that, so f would be, since f is differentiable, it is continuous, so fx is very near to fx naught, right? So fx minus px will be some constant times mod of x minus x naught, which is less than delta, right? Right. So that gives you the closeness. Did you get this comment? You see here, px minus fx naught is actually some constant times mod, if you take less or equal to some constant times mod of x minus x naught, right? Because x minus x naught is present everywhere.
Yes, sir.
Now, right now this fx naught is very close to fx, and that gives you px minus fx is less or equal to uh, epsilon times this one, right? Epsilon times epsilon plus some constant times mod of x minus x naught, right?
Yes, sir.
Yeah, so you see that would be the first order of approximation, and that's what it is here. Now if you want to see the derivative, you have to do this one again. If you look at a p prime x, so this goes away, you will have f prime x naught only here, and the remaining part will have x minus x naught, right? Now p prime x naught, p prime x minus f prime x naught will also be modulus less or equal to some constant times mod of x minus x naught, right? And since f prime is continuous, so f prime x, when x is near to x naught, f prime x is near to f prime x naught. That gives you the approximation of order 1. This one. Does this looks a little better? No?
Yes, sir.
Yeah, so you can take the derivative and yeah, so maybe I should consider again the polynomial the same thing px, which is fx naught plus f prime x naught into x minus x naught and so on, plus fn x naught x minus x naught power n by factorial n. Now if you look at this mod of px minus fx naught, right, which will be mod of x minus x naught times mod of f prime x naught plus however fn x naught by factorial n by x minus x naught power n minus 1, right? So this will be less or equal to some m times x minus x naught. So this is you see very close, right? When x is close to x naught. Now since f is continuous for every epsilon greater than 0, there exists delta greater than 0 such that mod of x minus x naught less than delta implies mod of fx minus fx naught less than epsilon. So continuity at x equal to s naught. Now this 1 and 2, 1 and 2 gives us, by using triangle inequality, px minus fx, which is less or equal to px minus fx naught plus fx naught minus fx, right? Now this part is less than epsilon, so this is less than epsilon plus, and this part is m times x minus x naught, right? Which is nothing but epsilon plus m delta, right? Right. So that this gives the zeroth order of approximation. Is this clear now? So this is the first one. If you look at derivative of a p prime x, what is p prime x? Px is this one. P prime x, this part goes to, this part is constant, so goes to, this is 0 derivative in the derivative. So this is f prime x naught plus, then there will be f double prime x naught times x minus x naught plus so on, right? Plus fn x naught by n minus 1 factorial x minus x naught power n minus 1, right? So your derivative will be on this side only because the coefficients are constant. So again, this p prime x minus f prime x naught, this is equal to less or equal to m times x minus x naught, right? Some m tilde, or maybe m1, yes. Right? And since f prime is also continuous for every epsilon, there exists delta greater than 0 such that, so you can pick that epsilon right here. So that it will work, both the cases will work. So there exists delta such that mod of x minus x naught less than delta implies mod of f prime x minus f x naught, f prime x naught less than epsilon, right? Now you put delta 1 here, and consider this same epsilon, so you'll get the approximation 0th order and the first order together, right? Now this will give you by triangle inequality mod of p prime x minus f prime x is less or equal to epsilon plus m1 delta 1. Okay? So similarly, you will get the approximation. That will give you that this polynomial will approximate up to the order n.
Sir,
Yes?
sir, how can you say that M0 or M1 exist? I mean, the function f dash x0 plus dot 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 fn x0 by n factorial x minus x0 to the power n minus 1 is bounded.
Right, that is bounded because I mean you choose a small neighborhood of x naught, right? So except that f prime x naught other part goes to 0 as you go as you take x near to x naught, right? So this is a bounded function. This is bounded on any interval. It's a polynomial, right? So you take a big
Okay.
interval AB and take the bound. There's no problem, right? So you choose a big interval where x naught belongs to x naught belong there in AB, let's say, where f is defined, and this would be bounded. Clear? Yeah, because up to
Okay.
fn, because what our assumption for the approximation is this all are continuous. See on the interval AB. We can choose the maximum on this interval AB, right? That m could be maximum of this interval of of this function, whatever remains here. All right, and this is a polynomial, hence continuous. So on a compact set, it is bounded, right? Is this clear? Similar argument gives us. So here one more line. Taking delta tilde to be minimum of delta and delta 1, we get the approximation of order 0 and order 1 on this minus delta tilde to delta tilde, right? So this x naught was there, so this is on x naught minus delta to x naught plus delta closed. Well, here we took less than delta, so we put it open, but one can make to as a closed interval. There will be no problem. So here you shrink a little bit here so that it will be lesser equal to and still it is true. All right. So we can proceed similarly. Proceed similarly. So this is so order one would give you. Sorry, I mean this is approximation of order 0 and order 1. Order 0 is contained in order 1. So we don't need to write this one. So approximation of order 1 is good enough. So we can proceed similarly to get the approximation for f in a neighborhood of x naught of order order n by p by the polynomial p. All right. So note here, the important point is that you can approximate only in a small neighborhood. So this neighborhood, this is a very small neighborhood. It is not true globally, which means in a big neighborhood of AB, this approximation is not true. Or in the whole closed interval AB, this approximation P will not approximate A. Right? This is true only locally, which means there exists a neighborhood around the origin here, on which you get the approximation. This is important. So the point is, we can write, write fx to be px plus rn plus 1 x on x naught minus delta to x naught plus delta. So this is the error term, the remainder term. Okay. So you can always write it. So this is, so what does it mean? It means define, so we don't know what Rn is, define Rn plus 1 x is fx minus px. All right. So this is what it means. We have created a new notation, but it is just the difference. It is supposed to be small. What form we don't know. Okay. So the interesting point is that in the assumption which we took here, that fn are continuous, and if you assume this fn plus 1 exists, then Rn can be given in terms of n plus 1th derivative of f. So if we assume f has, we already assumed f prime up to fn are continuous on the closed interval AB. Apart from that, if we assume if n plus 1 exists on closed interval AB, we don't need closed interval. Open interval, existence on open interval is good enough. Then this remainder, this is called remainder term, this Rn plus 1 can be given in terms of the n plus 1th derivative of f. That is the most interesting step. Okay. So we'll go to the proof of this one, what the form of Rn will be. So before that, we define few notation. This sometime use. So this is big O and small o notation. So suppose f and g are two functions in a neighborhood of x naught in R, and f is big O of mod g, or so we say, if there exists capital M greater than 0 such that mod of f by mod of g is less or equal to m. So this is, there will be x here, fx gx for all this is near x naught. So we need a point here. So where this is true, this is not true globally. For all points x in a neighborhood of x naught. Okay. We say f is small o of mod g near x naught if for every epsilon greater than 0 there exists delta such that mod of fx by mod of gx less than epsilon for all x belongs to x naught minus delta to x naught plus delta. So what does it mean? For every epsilon there exists delta such that mod of fx minus mod of fx by mod of gx less than epsilon for all x's. What does it mean? Limit x tends to x naught mod fx by mod gx equal to 0. Right? So this means it. Yeah, is this clear? Any question? Yeah, any question till now?
Sir,
Yes.
doubt. So, sir, I was just wondering if you are given an order up to which you want to approximate a function, and if
Mm-hmm.
uh, and if you're given the point at which you want to approximate the function, does
Right.
do these two parameters uniquely fix a polynomial which would approximate the function?
Oh no, there might be other polynomial which will approximate near x naught. Right? There might be other polynomial. So here px, if you add px is here, px is given like this, right? So if you add some other x minus x naught for higher power with it, that also will approximate.
No, but if we fix the order up to which we want to approximate the function.
No, that if you add higher order, it will definitely approximate up to lower order.
Okay, then I was confused because I thought like if you have n derivatives of the function at that point, then that's n which should uniquely fix the polynomial, right?
No, this is a uniquely fixed polynomial. This polynomial given this one derivative, one polynomial we can fix, right? This polynomial of this form, polynomial of this form is fixed. So what was our conclusion last time? It was, see, if you get this kind of polynomial of this form, then it will be fixed. So here, if you look at polynomial of this form of degree n, same form, then these two polynomial will be fixed. But the point is, there might be other infinitely many polynomials which will approximate a up to that order. There is no problem in that. So, but the derivative, if fixing derivative, you get one polynomial, right? In terms of, I mean, taking the derivative under consideration, there might be other. If you just change a small one for each of the derivative, that will also approximate.
So could you repeat the last point? How there might be other?
Also, you here you put some very small epsilon here in the derivatives, plus epsilon times x minus x naught plus epsilon times x minus x naught square and so on. Or any one of them, you add something that will also approximate. Or you add some higher order x minus x naught term that will also approximate. But the standard way to construct one is this one, right? Which will, the derivatives will also match. That is the point. If you match the derivative, then the polynomial is unique.
Oh, okay. So there will be arbitrarily many which are arbitrarily close.
Right.
Okay.
But if you match the derivative up to that order at x naught, then this polynomial will be this polynomial up to that order will be unique. Do you see the point? If you look at a higher order term, the derivative is zero here, there. So that will not contribute up to in the derivative. So it will match up to order degree n only. So a polynomial with this coefficient, right, up to the order n will approximate, not just approximate in this sense, but it will have the derivative the same as the derivative of f. And if you do that one, then up to that order it will be unique. Is this clear now?
Yes, sir, it's clear.
Okay. So now next task is to find the remainder. Mr. What is this remainder term? So maybe I'll just state it today. The next time we'll prove it. So this is very important. Telus theorem is very important. It has multivariable analog as well, from where a lot of things one can get. A lot of geometry arises from there. So the theorem is, assume f from AB to R continuous together with a prime dot fn. So f1 fn continuous and fn plus 1 exist on AB, then fx equal to px. So p is the above form plus Rn plus 1x. So the approximation holds actually near the point x naught. So for x naught in AB, approximation hold near x naught, but this one actually is true. So Zeroth term will not be small outside a small neighborhood. So this is true where Px is defined above, and Rn plus 1 has the following form. So there are two forms which can be both of them are true. So Rn plus 1x is this is x minus what happened? X minus x naught power n by n plus 1 by factorial n plus 1 times f n plus 1 c for some c lies in where? X naught to x. To x. So this is x naught is fixed. So in this segment, x naught to x c lies. This one and this one. So this is not different. These are the same. So both of them have. This is a different writing style, different writing in different form. So this is x minus x naught power n plus 1 minus theta power n by factorial n f n plus 1 a plus sorry, this is x naught plus theta times x minus x naught, where 0 less or equal to theta less or equal to 1. It's actually strict. Right. So what is this? This is Lagrange's form of remainder. Form the remainder. This is Cauchy's form of remainder. All right. So these are, so px plus any one of them is true. So these two not different. They are equal. Just it is you are writing c to be c x naught plus beta
Sir,
times
why
x.
x naught is smaller than x?
What? X naught? Oh no. This is, then it will be or x to x naught. Okay. Oh, so this is, you are right. So this is or x to x naught. Right. So x can be smaller than x naught. Also, in that case, it will be just line joining, segment joining x and x naught. Okay.
Sir, in the Lagrange's form of remainder, why x naught is less than x?
Oh no, this is not true. X naught may not be less than x. So see, C belong the segment joining x and x naught. X naught may be
Sorry, sir,
smaller.
I couldn't hear you.
Oh, so x naught. See here, I put x naught comma x. Do you see this red color stuff? X comma x naught. Hello. So C will belong to the segment joining x naught and x. So it is not that x must be bigger than x naught or x must be less than x naught. X will lie in the neighborhood of x naught. Well, x naught x can be lying anywhere, but C will be lying in the segment joining x naught and x.
So this f of x is equal to p of x plus rn plus 1 of x holds for all x in AB, right?
Right, this is true. This is true, but Rn is not smaller except in a neighborhood of x naught. So you will not get the approximation if you go beyond a small neighborhood. Okay, the approximation part. So Rn will not be small, error term will be bigger. If you go further, I mean, if you leave a neighborhood of the x point x naught.
And the form of Rn changes with change in x, right? That is the tricky part. Is that the
Oh yeah, it depends on x. Rn is a function. It depends on x, and the c is also depending on x.
C also depends on x, yeah.
C also depends on x. C lies in the neighborhood. So you see this n, if you choose n equal to 1, or maybe yeah, n equal to 0, you will get back this mean value theorem, right? Using n equal to 0, you get the mean value theorem back. Right here, so R1 is just x minus x naught time f prime c. Right? That is what. And px will be just f of x naught. So px, what is px? Px is this one. See, px will be f of x naught if your n is 0. Right? So px minus px naught, fx naught, px naught, or yeah, fx minus fx naught will be x minus x naught times f prime c. C belongs to this x comma x naught. Yeah.
So here, x does not have to be in a neighborhood of x naught.
No. Here, for this theorem to be true, it is true for all x in AB. So open interval AB. This is true for all x in open interval AB. But the point is, this one is bigger when you go leave a small neighborhood of x naught. So you will not get approximation everywhere. the form will be there, right? So mean value theorem is true for every point in AB, right? We will apply mean value theorem. So this is true, but the catch is the approximation does not hold everywhere because the error term becomes bigger. Is this clear? So what remains for us to prove is the form of this Rn plus 1. All right? Okay then.